like to thank our presenter tonight, who's going to be Jordan Moran from Cullum, USA, who will be talking to us about the fundamentals of sound isolation and acoustics. So first, I'd like to say thank you all for attending and listening to me prattle on for an afternoon. I have a master's degree in acoustical engineering from the Institute of Sound and Vibration Research in Southampton, England. As you can tell from my accent, I moved here because of my wife being American. That's just a bit of background. Former design engineer for gas turbines and large rotating machinery, acoustic packages. So that's enclosures. We're talking about enclosures the sizes of buildings. Ducting, we're talking about ducting the size of this room. And how do you get that down from 140 dB or 100 dB down to 85 or 40? To my credit, I have the world's quietest gas turbine package ever designed in Huntington and Peterborough, but that's by the by. When I moved to America, I came on as a consulting acoustical engineer. So that's where I got sort of a very big exposure to everything, specializing in acoustics of industrial spaces, but really I consulted on all manner of problems using, obviously, my degree as my credentials. And then I'm a former IAC Acoustics representative. So IAC Acoustics, you've probably heard of. They were at one time the largest provider of doors, windows, and everything else you could get acoustic around the world. And we had Virginia, Maryland, DC, Georgia, and Texas. I somehow got co-opted from being an engineer into a salesperson. I don't know why. I guess it's just because I'm too talkative. Currently, Cullum USA, as I mentioned at the start, we represent IAC Acoustics in Virginia, Maryland, DC, North Carolina, South Carolina, Tennessee, Georgia, Florida, and Texas. We also provide, as I say, oil and gas equipment and flow conditioning. So we now, through our partnership with IAC, we can provide anything from a studio all the way across to a wind tunnel. For example, we just did NASA's vertical wind tunnel, their flow conditioning, and IAC did the test cell. So that's down in Virginia Beach, Staten Island. And because someone told me it was a good idea, I included some photos of my dog to humanize myself. Yes, Will is laughing at the back of the room. This was on his. My dog, Indy, she is meant to be a golden retriever poodle mix. She is not. I'm terribly allergic to her, but doesn't she look cute? Right, so the fundamentals of sound. Sound is a wave of energy that propagates through a medium. When I say medium, I mean space, right? Whenever I tap on something, sound travels through. It oscillates. Now, we typically show it as this wonderful wibbly-wobbly transverse wave, and this you guys should be very, very familiar with. You know, sound is just a bit that we can hear. Then you get into radio frequencies, ultrasonics, et cetera, et cetera. So it's all very similar, right? It's wave-particle duality. So actually, really, what it is it's a longitudinal compression wave of air molecules, when I'm talking to you, bumping into each other. No particle actually moves. The energy is just transferred one after the other, bumping in as it goes along. Always bear that in mind when you're trying to understand the way that sound works, because if you think of it as a wave, you might think, you might go in the wrong direction. Now, again, I'm probably talking to a room of very clever people who know about radio frequencies, so you're probably very familiar with the idea of long frequency waves bending around the Earth, short frequency, beaming, and thus not going as far. But when we talk about walls, it really informs why walls, ceilings, windows, doors, why they actually stop the sound and why it's actually useful. So, basic partitions. I'll keep using partitions because I like to keep it general, but when I say partition, I basically mean a wall or a ceiling or a floor or a window or a door. Doors are a little bit trickier, so I'll come on to that later on. The way that energy is lost is via heat. So as those particles bump into each other, they lose heat, or they create heat, should I say. So how do you govern how much energy is lost? It's mass. You may have heard of mass law. Maybe some people who have done a little bit of investigation online. If you don't know what mass is, cast your minds back to high school level physics. It's density times volume. We can think of it in practical terms as weight. It's not truly what it is, but the rule of thumb, weight. How heavy the partition is. So density can be thought of as the number of molecules in a given volume.
Why does this govern acoustic performance? More molecules in between the source and the receiver, the more times they bump into each other, and the more energy will be lost to heat. So when you see mass law, you'll see it represented as surface mass. Surface mass is just a given thickness. I say all of this because practically what that means is at a given thickness, more dense things will stop more sound. So if you have an inch of concrete, it will stop more sound than an inch of wood. We're talking thickness here, not how big the wall is. Conversely, or at the same time, at the same density, so say you have, sorry, I think I've said these the wrong way around. Yeah, same density. Yeah, sorry, same density. So if you have lead, let's say, or concrete, the thicker you make it, the more sound it will stop. So what does this tell us practically? We want heavy things because heavy things stop sound. And if we start making things thinner because of space constraints, we want to make them more dense. So that kind of gives you a feeling for why we don't just do single layer of drywall. We do multiple layers of drywall when you're trying to do a space. Mass is a very limiting factor though, because if you double the mass of a partition, you only get a 3 dB increase, or decrease, should I say. 3 dB increase in performance, 3 dB decrease. So say I have, I don't know, 2 layers of drywall. I say, oh, you know what, I'll add another 2 layers, because that should give me loads, because the first 2 layers got me, I don't know, 30 dB of reduction. So you go, I'll add another 2 and I'll get another 30 dB. Doesn't work out like that. You'll just get 3 dB of reduction. Now again, I'm assuming everyone kind of understands dB because radio waves, but yeah, decibels, the unit of measure for sound, very similar to anyone else's dB, it's just your reference is different. Like I say, mass becomes limiting because I can only make it, every time I double the mass, I'm only adding 3 dB. So if I want to go from 30 to 60, I've got to make things double and then double again and then double again and then double again till I've got a wall that's as big as this room and not very useful. So when I describe single layers, you use mass law. But when you start getting into higher performing partitions, you want to get things that have vibration isolation. So isolating one layer of the panel from the other. This is why most studios are built out of double stud. Again, if anyone's cut the wall of their studio open for any reason, you have double studs or a room within a room concept. You don't just have a foot of concrete. A foot of concrete is pretty good, but you can achieve the same amount of performance with a more complex partition. So vibration isolation means that the energy that's transmitting through the partition is being lost in that vibration break, and then it has to go through the next layer. So there are 2 layers completely unconnected. They are perfectly isolated. You'll get 100%. So just to reiterate that, if you have 1 layer of drywall, it stops 30 dB. You have another layer of drywall, if you don't glue it together, and you just put it in a perfect space with a vacuum between the 2 of them, the 2 will perform 100% of their original. So you get 30 and 30. You get 60. Yay! That's what we all want. Fortunately, in the real world, walls don't stand up by themselves. You have to connect them together, and you can't achieve a perfect vacuum between the 2 of them. So then you get into, well, practically, what can you do? Which means you start connecting. So I just mentioned this, performance, mass law. Glue your 2 pieces of thing together, be the concrete, wood, drywall, spaghetti, I don't know. Each time you get a 3 dB every time you double the mass. So you have to get thicker and thicker and thicker to get small increases. So you say, well, you know what, I'll use some kind of rubbery stuff in between them. And this is kind of, floors are a very good example of this. You have your original concrete floor and then you put some kind of vibration break and then you put your finished concrete floor, something like that. That's a good descriptor of that. As the sound travels through, this vibration, will absorb some of the sound, turn it into heat before it goes to the next one. This one is much better because you've got small attachment points. So every time the sound comes from one side, it has to wobble those orange blocks to get to the next one. And not to be silly, but how wobbly those orange lines are will govern how good of a performance that panel is. And the final one is perfectly isolated. The one I was just talking about, those are perfectly isolated. It would be layer A plus layer B in terms of acoustic performance. How I mentioned, your studios will usually have double studs isolating each layer of drywall from the outer layer. That's trying to get as close to this as you can, right? Because you use a 4-inch stud on this layer of drywall, use a 4-inch stud on the layer of this drywall, and those two studs are not connected. So the sound has to go through the first layer, then go through the air, then go through the next layer. So everyone following me so far? Just give me a cheer if you are. Yay! That was just for everyone on Zoom to know that there are real people in this room. So that's where your performance comes from. And now we get into how it's described and how people in the industry start hoodwinking and fleecing people. And I will come back to this repeatedly through my presentation, because my biggest bugbear with the industry, apart from architects, as I was saying earlier, is the half-truths that we acoustic vendors tell you or kind of allude to or make you believe, and it becomes kind of so ubiquitous in the industry that everyone just thinks that's the way it works. So performance definition, if we really get to the fundamentals, in academic circles, we'll call it transmission loss, or TL. That's the amount of dB that the partition stops. It can be as simple as taking what is on the source side minus what you get on the receiver side. So I have 100 dB on one side of the wall, I have 50 dB on the other side, I've got a transmission loss of 50 dB. That's what we refer to it as when we're trying to do acoustic calculations. But you'll hear and you'll see in people's test data and on people's one pages of why you should buy this product, things like STC, NIC, ASTC, AFSTC, R-W, D-N, and a whole bunch besides. And that's just for sound isolation. Obviously, you're probably more familiar with absorption, how much fluffy stuff on your walls stops sound. So STC and NIC are the ones that you should really talk about. All the rest of those ones I list, RW is the European equivalent. A and FSTC are field measurements. So you want lab test data, let's be honest. STC is a single number value which characterizes transmission loss performance of a partition in a laboratory setting. If you see NIC, and there are a few asterisks to this, but if you see an NIC on a piece of literature, it is a single number value which characterizes transmission loss performance in the real world. So if someone gives you test data that is NIC, it comes with a lot more caveats because it was a real world measurement in a genuine environment, which could be good if your studio or whatever you're building is exactly the same as what they built to test their thing. STC, however, is a lab, but again, that's a laboratory setting. So that's an idealized, perfect solution. So the truth is that your performance will lie between the two. Now, you notice I'm mentioning that it's a single number value. One of the big mentions that mistakes, should I say, people in the industry make is that they are not an average, right? People will tell you that STC and NIC are an average of performance at each frequency. Again, I'm talking to people who are very familiar with frequency. So as you can imagine, transmission loss of a partition is frequency dependent. Depending if I'm at a high frequency or low frequency is dependent on whether my partition stops. You know, a heavier partition is good at low frequencies and high frequencies. A lightweight assembly is good at high frequencies, but not low frequencies. So the transmission loss of a wall or a floor assembly varies wildly depending on which frequency you're at. And then guess what? We as vendors tell you, well, my STC is higher than his, so mine must be better. And it's an average. So it's basically the average performance. Just take it as a dB value and be done with it. That is not the case. It is a misnomer. If you really wanted to be mean to people, it's a bit of a lie. And as I mentioned, NIC is typically worse than STC because of your build conditions are never as perfect as the laboratory conditions. Because we as vendors will spend about 3 days in the lab getting our sample ready to be tested. So we will go through and we'll block up every single little hole, everything that could degrade our performance. And some people even put duct tape in certain places and do some, not so great things. But you didn't hear that from me, just to be clear. I know this is recorded, so I probably shouldn't say those kind of things. We don't, and that's why it upsets me, because as you can tell, I'm very scientific driven. It's my background. So I want the numbers to reflect what the real world is. I have an analogy for STC, which, as I said, is the single number that everyone will tell you. My STC is 50. His STC is 49. Mine's better than his. The classic top trumps version of sound control. Fortunately, you can't quite see things because of my name being in the way. I think of STC as an analogy to overall MPG when you're buying a car, right? At the lot, you'll see a number on the window that says, I don't know, let's say 30. MPG 30. And then they'll have two other numbers, which are city and highway. And city will be 25 and highway will be 35. Right? And then look, we're overall 30. That's kind of what STC is. STC is the overall MPG, including city and highway, all those different frequencies, represented as a single number. But in your world, you might drive more on the highway. So you might want a car that has the best MPG on the highway. Or you might drive a lot in the city and be fixated on, well, actually, I need city MPG. I don't care about highway. If that's brought the average up, that's not useful to me. Same thing with STC. In that situation, I'm talking about frequencies. City MPG is high frequency. Highway MPG is low frequency. In your specific application, you might be next to an airport. You need low frequency performance. You don't need STC 60. You need 50 dB of transmission loss at 63 hertz or something like that. So you don't want to look at a single overall. You want to look at the individual transmission losses. You want to look at your individual MPGs. And again, you might pick a product that has a slightly lower overall MPG, but has a much better highway or city MPG because that's where you need the performance. That's the transmission loss that you need. That's the frequencies you need to stop. And in broadcast spaces, the best one I get into is things like mechanical noise and transformer noise. So obviously, if you have a partition that has a good STC but is terrible at 60 and 50 hertz, you're going to have hum that comes through your wall, as it were. Obviously, we'll ignore the messing with all your cabling and all that stuff, but those kind of things that transmit through walls and they're really hard to treat. The STC might look really good, but at the low frequencies you need, they're terrible because STC is a curve fitting. That's just an explanation of what I was just talking. This is what an STC graph looks like. The green line is the actual measured data. The purple line is the STC curve. And genuinely, to get STC, you move that curve up or down until a certain criteria is met, and that's what the number is. So this curve, when we take measured data, you move this curve up and down until you get just the right place, and then you read what it is at 500 hertz, and that's your performance. So it's not an average, it's a curve fit. And being a curve fit, it makes it really hard to translate into real world performance. There are some rules of thumb. You lick your finger and you say, STC 50, probably going to give you about 46 dB of reduction. Yeah, that sounds about right. Again, STC is not a direct relation to how much sound it will stop. And dB is what you're actually trying to get the performance out. You're trying to lower the dB from one side of the wall to the other. This slide just goes through the test standard and how it works. Again, I've put a lot of information on the slide because I expect you to be able to reference this. I assume Will share this presentation afterwards. And so you can go and read through a lot of this stuff. But basically, like I said, it's sound on one side, measure it on the other, and that's your transmission loss. It's a pretty simple measurement. NIC, as I mentioned, take a drink, is the real world test. This is an extract from the standard for doing it. D is what you're trying to measure, sound through the partition. F is what we call flanking. Flanking paths are one of the biggest things that kill studios or well-designed spaces. Because someone designs a really good path for sound D to go through. Hey, thumbs up, this is an STC 400. That's make-believe, but this is really good. But then no one figured out how it was going to attach to the host facility. And so there's a little gap down here, and all the sound goes around our really good partition wall and gets back into my studio. That's the number one complaint and issue I have seen throughout the years I've been working. People not considering flanking paths. NIC is a great measure of that, because if you try and measure this wall, you'll actually measure the overall performance from one room to another. So I do recommend, if you're going to specify spaces be tested, NIC is a really great way to figure out whether the build quality is up to snuff. Was it actually built how it was meant to be built? Because NIC includes all those flanking paths. Rules of thumb, NIC is typically 5 to 10 dB below. It should be 5 to 10 dB or 10 points below the lab. If anyone tells you that their product performs within 15 points, their product is garbage. Just don't go with them. Because there should be no world in which you can test something in a lab and then you allow yourself 15 points of failure. Good companies will specify, when measured in the field and everything else being good, 5 dB or 5 points of the measured. That's what they should be holding. That's the standard you should be holding them to. Drywall partitions typically are 10 to 12 points worse. The answer is drywallers just don't know what they're doing when it comes to acoustics. The biggest degradation in performance I find is drywall mistakes, ventilation, penetrations. I'll come on to this in a second when I talk about existing spaces. So everyone follow me fundamentals. I'll switch pretty interchangeably between STC and NIC, but as you know, they're basically the same measure, just one's in the field, one's in the lab. So, you buy a product based on a lab test and you put it in your space and you get an NIC. So I'll talk about STC and NIC as I go through these things. And I'll also talk about dBs, because really that's the performance that you're looking for. Stopping however many dB on one side and coming to the other side. As I say, I talked about the fundamentals, but this isn't a lecturing class. We're not back at school. So what about my studio? You're thinking, hey, that's all well and good. I've heard this, but what does that actually apply to? So we've got walls, ceilings, floors, doors, windows, and ventilation. The fundamentals of every room, any room, doesn't matter what it is, every enclosure, every large industrial plant, every jet engine test facility. These are the places where sound goes through. This is where you must stop them. So considering each of these elements, again, I see a lot of attention paid to things like walls. I see less attention paid to things like floors. People just go, it's a 6-inch slab. What else can we do? Well, 6-inch concrete slab only stops so much noise. If you've got high levels of noise in the floor below, you're going to need to think about that. Doors and windows, people typically get some idea of. Ventilation, always ignored. Hopefully, again, the people I'm speaking to in this room are very familiar with the idea of air turbulence messing up their microphones. If you're trying to take, you don't put ventilation over the top of where you're speaking, over the top of microphones, because you get wind distortion, things like that. So again, ventilation, one part is the effect it has upon your actual measurements, or should I say your broadcast, fidelity. But the other thing is how much noise goes from one space to another. Right. Jumping into, if you have a big pocket of money and you have new build walls, fundamentals that I went through apply to walls beautifully. Isolate as much as possible between inner and outer layers, put in as much mass as is feasible, and you'll get in the right way. So thick and heavy walls will stop lots of sound. Put a big concrete wall up. However, you can get similar performance with lighter weight construction vibration isolation included. Double stud partitions, room within room construction. Again, I'm hoping that these are kind of phrases that you've heard bandied around the industry before now. Penetrations, not the fun kind. So we're talking cable pass-throughs. Anything that goes through the wall, that's where specification is always lacking. So again, you specify, you say, hey, okay, I definitely know I need 3 layers of drywall on the inside, a layer of studs, insulation, another layer of studs completely isolated, and then another 3 layers of drywall. The guy builds it correctly, and then it comes to the day when they've got to run, I don't know, your fiber optic through the wall or something. You're not using a computer floor. You're going straight through the wall. And you just start drilling holes. Well, suddenly, that's where you get loads of leakages, and that's where you get lots of performance degradation. That line about low frequency performance, I mentioned you guys will want low frequency performance if you're trying to measure anything or try to record anything with good fidelity. When it comes to penetrations that we're just talking about, the key here is minimize. Minimize the number of things going through your wall. And even if you're using a computer floor, right, so raised flooring where you have access hatches, very common. Even where that cabling comes out, it comes out typically usually underneath the door. And so you have this really great door and you have this really great wall, but then underneath the floor, there's a great big hole where all the cabling goes through, which isn't sealed in any way, shape, or form. And so suddenly you get an acoustic door that is doing nothing because all the sound is going whoop. So if you're going to have penetrations, if you're going to have pass-throughs, you want to minimize them, you want to stuff them with foam, and it's as easy as foam. That's really all you need to do. Take a 6-inch block of foam, shove it in whatever hole you've got. And the 6 inches of foam will act as like a RF shielding, how we do it in our rooms. We use a long pipe and stuff it, and it decays as it goes through. So good sealing. Again, I will mention good sealing regularly throughout this entire presentation. And you think your contractor is going to do it, but again, your contractor is not an acoustical contractor. And even if they say they are, they're using probably a subcontractor who isn't. And that subcontractor and his crew of guys, or her crew of guys, just puts up sheetrock to block the light from one room to another. That's how they think about it. When they see this wall, they go, all I've got to do is make it look smooth and nice and good. I've seen things as stupid as triple layer partitions where, say, this big lighting rig, right? So what people at home can't see is that there is a bank of 12 light switches in 2 separate boxes. That is a really annoying detail to do 3 layers of drywall on. So what they do is for the 2 base layers, they will just cut a big hole. So you'll have this big hole, and then on the final layer of sheetrock, they take the effort to cut the perfect little slot. And it looks, if you were to just approach it, you look at it, you could take this faceplate off and go, oh yeah, that's good. That looks good to me. But behind it, there are 2 great big holes in your triple layer assembly. And that becomes, again, a good leakage path, poor sealing. So, you've really got to keep on contractors about these details must be followed to the letter of the law. No ifs, ands, or buts. And I recommend, I guess you're the kind of people who do this. Be in your studio when it's getting constructed. Look at what they're doing. Walk around with a clipboard. It seems silly and it might piss off the GC, but it's sometimes the only way you can prevent contractors who don't really know what they're doing from messing up a really perfect design. Because from what you've designed to what gets built in the real world, there is sometimes a very large chasm. I will mention this, and it's on several of my slides. I recommend consulting a professional, someone who is a studio designer or an acoustical consultant. Please don't all look at me. For construction specifications, again, like I said, they'll specify the best thing. You just need to make sure it happens. And as always, watch your drywallers, check them. This is everything I was just saying. It's on every single slide, I think, when I talk about new build. Just watch what they're doing. because they just don't do it right. So, improving the walls. As I said, most of you probably don't have a big piggy bank waiting to build a new studio and can follow those guidelines of designing the perfect assembly. Again, I didn't put up wall assemblies for you to look at because really, if you need wall assembly details, there's libraries of them out there on the internet, or like I say, work with a consultant to give you the right spec for your room. I'm not going to give you like a cheat sheet. So assuming you designed it correctly and it was built correctly, the loss of performance will be either due to poor construction execution or basically weak points, which I don't really illustrate in that sentence, but it was designed correctly, it was built with some deficiencies, and you will see slowly bits and pieces of sound leak around. When you're trying to spot fix why my studio is too noisy, when it comes to the walls, I'll come on to each section. This thing, I'm going to go through floors and ceilings and doors and windows. What should you be looking for? Look above your ceiling grid. Look around door frames and penetrations. Look behind the baseboard. Yes, peel the baseboard off your wall. And if you see this nice little like, 1/4-inch gap with a bit of cork in it, they've probably not properly interfaced your drywall with the floor. Because a good acoustic design should have, in effect, an isolator underneath the sheets of rock, sheet rock, in between your floor and your wall.
What do you mean by an isolator?
Isolate, so usually it's either some kind of like rubberized system. Some drywalling systems just use a heavy, dense mastic. But in other times, like I say, you'll know it's not been done because a lot of drywallers, when they know there's baseboard going on, will not do anything to the bottom of the drywall. So when you peel back the baseboard, you'll just see, in effect, a rough. It'll be filled with dust and dirt and debris, but it won't actually be corked or isolated from your floor, which means you're getting a little flanking path underneath the perfect wall that you've just built. And it goes through the light gauge stud and out the other side.
I like that term, flanking.
Flanking
Is that used in cricket or something?
Yes. Well, actually, in rugby, there is a flanker. Not to be confused with something that begins with W and is
right,
also a British term. I was told I was too short to be a flanker. It's still a wound, so thank you for opening that up. Going back a couple of decades, but still it stings. But these are the areas that get neglected, and you can solve it with corking and packing. For small penetrations or small flanking areas, it really is as simple as that. And I have seen wall assemblies be boosted by 5 dB of performance just by sealing penetrations. Correct. Just by little small gaps. I will show you an interesting video. There's a really cool thing called an acoustic camera. And it allows you, very much like thermal imaging, it will show you where the sound is coming through. Now, they're rather expensive to buy, so I don't recommend anyone buys one, but you can rent one reasonably cheaply for a few $1,000s these days. That's how cheap they are. And you can point it at wall assemblies and see where the sound is coming through. So recently I was consulting on some conference rooms in North Carolina. Now, the picture's really gray and fuzzy, but where you can see those little orbs bobbling is where the sound is coming through that partition. You will notice I panned up and there was a big bobble at the top. I panned down and there was a big bobble at the bottom. This was a proper, good drywall assembly. And then the architect had shut this 1-inch single pane glass divider between each conference room to give, I don't know, natural light, something silly, I know that. The glass pane wasn't terrible, but it did degrade the performance. Where they had the biggest degradation of performance is that was a lightweight storefront type assembly. So the bottom channel and the top channel, the glass just floated on small pieces of rubber. So all you had between those rooms at the bottom and top were 2 lightweight pieces of aluminium trim, or aluminum trim if you are playing in America. And consequently, this is the kind of flanking path I'm talking about before. Not only did the architect introduce a massive flanking path by putting a big piece of single pane glass, should have been double paned, could have been designed correctly. They designed the wall correctly. Why didn't they think about the glass? I don't know. Silly. But even with the glass insert, it shouldn't have been as bad as it was. The reason why it was so terrible was because of those flanking paths under and over the pane of glass through a lightweight assembly. That kind of thing that your studios, hopefully you don't have a big piece of glass that's single pane in between them. But those kind of under and over pieces, that's what we're talking about here, sealing up to the grid. I've got some other pictures. You can tell from the thumbs down, we do not like them. This is an audio-visual cutout. So as you can see from the Logi and all that, that was a visual display with conferencing tools and all these, like this fancy lectern. The person who cut it into the nice acoustic wall just cut it in. It was going to be hidden by the TV, so they didn't care. However, if you pull the TV out of the way, you will see that there is between a 1.25 inch gap all the way around that. So they've just chopped a massive penetration. Not to mention that that visual display unit is, or it's not the visual display unit, but the backer box to sink it into the wall is all lightweight. So you've got 3 layers of drywall that suddenly have, I don't know, a piece of, 14 gauge steel, which isn't very good, as you can imagine, with lots of holes to allow lots of cabling going into the wall. And lo and behold, when I pointed my acoustic camera at that, it just lit up. The wall was great, that penetration, and they made the mistake of actually in certain rooms doing those back to back. So the only thing between those 2 rooms was just 2 layers of thin gauge steel. Massive sound leakage. It was a terrible nightmare for them because every time they had a conference in one space, the people in the other space could hear it. Hopefully, your studios don't have anything as crazy as this, but it could happen. I mentioned lifting up your ceiling grid. If you have a ceiling grid, lift it up. If you don't have a ceiling grid, look. This, very hard to tell, but this is the interface between a structural column beam or that supported the roof, which has been sprayed with fancy stick-on foam to make it acoustic. Great. This is our, as I mentioned, pretty good acoustic wall. And then this is the conduit that they've just kind of roughly cut the entire top of the partition off and shoved all that conduit through. Can you guess what happened? All the sound went into the ceiling grid and then went to the room next door, following those wonderful electrical conduits. I will not just keep pointing out failures. I will show you something that's done right. See this? Well sealed to the top of the deck, with mastic caulking all the way along, well sealed into this very annoying I-beam. They've ran the drywall sheeting all the way up against it, masticed around it, and where they had multiple penetrations, they put one piece of PVC pipe, I think it was actually metal, but through the wall, and then ran all of their cabling through that pipe, which meant my only recommendation there was stuff it with some insulation. You know, this was an empty pipe. But that is how you should want to see your penetrations in your wall done. Collected together, put into one large conduit, a conduit that you can pack with fiberglass or foam, so that any sound that comes through that one singular penetration is stopped. And that's it, really. If you're trying to improve an original wall, and let's say that the wall is just bad. Again, I'm not thinking this is necessarily your studio spaces. I'm thinking if you're renovating conference rooms to turn into small podcast spaces, or, you know, sometimes you've all been in this situation. Sometimes you have a room that you have to improve. And the walls are terrible because they were never designed to be a studio, but you don't need it to be studio level. In which case, if you're trying to improve an original wall, there are several options available to you, and it all depends on how much space you've got. If you've got limited space and you need to retain square footage, put an extra layer of drywall on, separated by a vibration membrane. There are squeezy tubes of this called green glue. If you are looking for a specific product name, no, I do not represent it, so this is an independent thing. And that will isolate a little bit the extra layer of drywall. If you have a bit more space, I would recommend isolation rails. You will hear them referred to in the industry as R1 channel. They're a little Z-bend. You screw one Z-bend into the wall, one leg of it, You screw the new layer of drywall into the other leg. And what that means is it's, again, everyone at home can't see this, but I'm making the shape of a Z or a Z. You screw one into this, and when the sound hits it, it flexes like that. So it loses energy. You can also do that with a puck system like PAC, which is also available. Or if you have a lot of space, like I say, build a brand new layer of studs. New layer of studs, pack it with insulation, put on 2 new layers of drywall, and that will vastly boost any room you're in, regardless of how good the room is to begin with. So there are your 3 options if you're just trying to, you've plugged every hole you can, but you need to improve the walls. That's the way to do it. I mentioned ceilings. Ceilings are very similar to walls, except for the fact that you've got typically an issue with all the stuff that you need to put into a ceiling, like ventilation and lighting, and also you've usually got someone above you. So where possible, use the same construction of the walls. I've mentioned multiple times here, room within a room. When we do rooms within rooms, the ceiling is typically a solid drywall system, and it is using the same construction of the walls. When you use a drop tile ceiling, which does occasionally happen in studio or recording spaces, when possible, place all your ventilation, bar boxes, branches, whatever, outside. Really, you only want one branch going into the space, split to serve just your room. And where possible, use a dedicated unit. Do not hook up to the building's AC. 2 reasons for that. 1, lower CFM going through the system, so you get less noise from your ventilation to begin with. I can hear this ventilation right now because it's so big. And 2, you will get no crosstalk. I've been in several spaces. There is a studio called Stand Together, which some of you may be familiar with. It just got made in DC. It's for a non-profit. They're renovating an existing space, so they were kind of space constrained. They'd been using the same ventilation inside to outside. And so their studio could hear what was happening in the corridor next door. Because this register here transmits the sound down to the register over there. And in their case, it was the distance of 2 feet. So anyone talking in the corridor gets straight into your space. Not exactly what you want. But again, it's that problem of you've only got what you've got to play with. I mentioned here, think about what's above your roof. If you're trying to select a space to improve or change, think about what's above it. I've had several clients, not studio spaces, just conference rooms or things like that, who decided to put things underneath the gym. 1, why did you put the gym on the 2nd floor was my first question. But number 2, weirdly enough, there's not very much you can do. Big pounding weights hitting above you, or I don't know, the mechanical room, I've had that before. Putting your mechanical room or your elevator room directly above where you want to do a conference room or a broadcast, guess what? All of that noise is being transmitted through the ceiling, and you're going to have to do something really crazy to stop the sound from coming through the structural ceiling that's above you. Again, I've mentioned penetrations. You don't get many penetrations going through ceilings. This is more about coming in above the ceiling grid or at the top of rooms. That's what I mean when I say penetrations there. And as I mentioned, if you're building a new space, get involved with someone who's a professional. Do not rely on your architect to have the skills necessary to do these. Go and talk to a professional. Like I say, where you're located in the room is, or where you're located in the building is sometimes not what the architect thinks about, or your boss, or even you. You know, you think that this is the perfect space because it's got 1,000 square feet and it's a room that no one uses right now, but you forget that it's directly underneath the elevator. Suddenly you're going to have a lot of problems that you could have avoided if you just considered where you were building, when you were building it. Improving, again, assuming everything has been built correctly, it's going to be poor construction, same as the walls, exactly the same kind of recommendations. But with this, again, look above your ceiling grid, look for the interfaces between your wall and the host facility ceiling. Again, if you're using a room within a room, look at the joint between the 2 rooms. Caulking and packing, same thing I said before. And if you're converting an existing space, it's all about adding layers of drywall. Ceilings can be really tricky because if you've got a drop tile ceiling, there's not very much you can do. You can improve the tiles themselves, but it's always going to be a bad ceiling arrangement. So if the noise is getting into your ceiling cavity, you're going to have to look further down to try and stop the sound from getting into your ceiling cavity in the first place. If you've got a drywalled soffit, something like this, you can easily improve it by just adding drywall. Say that you've actually got a proper ceiling assembly that hasn't got lots of stuff in. You can improve it by layers of drywall and brand new ceiling assemblies. I have in the past, in some spaces, had to go into the space that's got the issue and basically on their rafters, the actual beams, install a whole new layer of beams and hang a brand new layer of sheetrock to try and deaden the noise from the space above. That was in some condominiums, to be precise. Again, hopefully your studio isn't dealing with this. But these are some great examples of what you can find above your ceiling grid and in your soffits. Again, this is just as true if I was to stick my head into this drywall soffit, I would probably see things like this. As you can see, double layer of drywall. Someone cut it to look at these conduits. Never sealed it back up again. So now you've got a big hole. Any noise that gets into that hole will spread up and down the wall. Two of these ventilation pass-throughs. You can see this one is double layer of drywall, double layer of drywall. But I can see the room next door. If this is happening above your broadcast space in your control room, and you've got lots of noise, it could be coming down the actual branch itself, or it could just be coming through a nice big hole in the wall. Again, this one really impressed me. As you see, ceiling tile grid below, and then just big enough for a man to step through. I don't know why they did that. They absolutely annihilated the acoustic performance between those two rooms. There should have been, if we talk about the STC of the partition, that partition should have been somewhere in the STC 55-ish range. It tested out as STC 30. Big performance drops from small holes. Even these ones in the middle, where it was just roughly cut drywall around a lagged branch of ventilation ducting, they were testing out of low 40s. That's a lot of performance lost just because someone didn't seal the penetration very well at all. If you can see a theme forming here, it is add layers of drywall and look for penetrations. It really is the number one way to stop sound and improve the isolation of your walls. When it comes to doors and windows, a little bit different. I'll come on to those. But when it comes to things like floors, doors, floors, walls, ceilings, it all goes back to those fundamentals. Making a wall, making it thick, heavy, dense, vibration isolated, and then make sure that it's actually built correctly with as minimal amount of penetrations as possible. You're building a new facility and you've got to figure out what floor. I'm going to assume that you're on the second floor, not the first floor. If you're on the first floor, we will talk about that. It's really complex when it comes to floors and acoustics. In theory, it should be quite easy. Make them thick. So if you use a 6-inch concrete slab, use a 12-inch concrete slab. However, vibration transmittance through concrete is what usually kills new build floors. I mentioned right at the start of this, I tapped on the table. I said, whatever I hit here, it travels down the table. Exactly the same thing with your concrete. Your concrete might be dead enough not to make a sound, but the vibration is still traveling down. So if you have, and I've seen this in spaces before, and I'll use the example of a transformer because it's nice and easy to understand. When you pour the bottom floor of a building, you pour it as one big slab because it's easy. A voice from above. So you're throwing down your one big slab of concrete, and someone starts mounting every piece of service utility onto it. So, you've got transformers on there, you've got steam pumps or boilers, all these different things that are for very important purposes. But they're all on the same slab as your studio. So any vibration that they create in the slab gets transmitted along the concrete, under your floor, under your wall, your great ceiling, and then just comes back up again. And it can shake you. Now, again, I give you an extreme example, but when we do jet engine test facilities, we have to do crazy things to the ground underneath so that people 3 miles away don't get their windows rattling. You can't hear the sound, but the vibration is still being transmitted all the way 3 miles away and shaking people's windows. It's that kind of thing that we're always trying to prevent when it comes to floors. So new build floors, it's all about not necessarily the acoustic performance, because if you're on the bottom floor, you're not worried about sound coming down or up. If you're on the second floor, okay, maybe you might have trouble with what's below, but I'm going to assume that what's below you is not too noisy. With new build, it's all about stopping vibration. So that means either one, you pour a separate slab for your studios. And this is the reason why I say second floors are so annoying, because you can't pour a separate slab for the second floor. For the base floor, I can pour one slab, put a 1-inch gap, fill it with some cork, and then pour a whole new second slab, which is just for your studio. On the second floor, I can't isolate pieces of the building from one another. So that's where you get into, if you start building on the second floor, you want to get into room within a room construction where you put the secondary floor on isolation pucks. So again, this is the idea of you can pour a second layer of concrete and put it on what we call jack-up pucks. Again, sorry for my accent. I know that I have a lot of when it comes to pucks. But basically, they're little rubberized pucks that go underneath whatever the floor of your studio is. And then you float everything in your studio onto the secondary floor. So walls that are connected to your ceiling. If you're on a second floor, that's how you want to do it. Completely isolate yourself from your host slab. And even if you're on the bottom floor, you probably want to do that anyway, because you probably don't want to worry about any annoying stuff. I mentioned computer floors earlier. Again, that's kind of flooring. Acoustically, computer floors are, I don't mind. Your subfloor should be the important bit. Your computer floor is just for convenience. Don't rely on it for acoustics, and don't believe anyone who tells you that they're really good. They're decent, but they're not good. And look at your ceiling, where you seal from room to room below the computer floor, because you don't want to run your computer floor underneath the studs. You want walls to go floor to ceiling of your host, and then your computer floor to fit in around. And you want to consolidate, as I was saying, all your penetrations to one place. And if you can't do that, seal them up all really good. And make sure you have a design condition for going underneath doors and underneath walls so that you don't end up with big voids. Very convenient for cabling, very painful for acoustics. You're basically just opening yourself up to degradations of performance. Then, if you're building a new space, contact a professional. If we're trying to improve a floor, it's tricky to say what your issues are going to be. If you've got low performance and you really find out it's your floor, I'd be surprised, number one. The only thing that it might be is things that are glaringly obvious. Like sealing between the host facility and the floor. It's unlikely that you'll have actual sound coming through your floor unless you can hear it. You're like, yes, it's the people below us. It's our noisy neighbors. If you do have the noisy neighbors, you just have to put in a secondary floor. That's the only solution you can really have. If it's poor design, you'll just have to put in that secondary floor and isolate it from the host facility. It's the only real solution. But like I say, 9 times out of 10, it's usually the doors that are the problem. 9 times out of 10 is probably a little bit unfair. Doors are 70%. I'll say 70%. 70% of studios that I see having trouble will be due to doors or windows. Or, again, penetrations, usually they've already been sealed up pretty nicely. I do mention, I said cut the slab. If you are able to do that, that's more of something that you can do in smaller, lower, again, not broadcast level spaces. In lesser spaces, you can do things like, if you're on the ground floor, cut the slab around your studio, fill it in with some weatherproofing, and you can do that. Continuing on, we've done floors, we've done walls, we've done ceilings. I mentioned a lot of things that were problematic, like ventilation pass-throughs and cabling pass-throughs. I mentioned the idea of crosstalk or bleed. That is sound that travels through the ventilation ducting and into your space. You also have system noise. That's the noise that, if we all stay quiet for a second, we can all hear. It's that low rumble above our heads. In some cases, it's a high-pitched whistle. You've been in spaces where you can hear the air conditioning. Those are the two ways that acoustics is compromised. Either sound travels along the duct and messes up one room to another, or your system is so noisy that you actually just can't get a good recording. I'm busy doing some work with the Library of Congress at the moment, the National Library Service. They're the people who record books for the blind, if you didn't know, or visually impaired. And their whole specification is all about ventilation being low enough CFM, that's a flow per minute, to not impact their recordings, because they have to have incredibly crisp, clear recordings so they can be played at double speed. Because apparently, when you listen to a book, you listen to it faster than I talk. Though I think I talk quite fast. Sound travels along duct from one space to another. To solve this, whether it's a new or an existing space, so this applies to both if you're building a new space or if you're building an old space, you have two choices. You can either have a Z-duct, that is the one shown in the bottom right-hand corner. Quite literally, you just put a bit of a kink, you make the sound go around the corner, and you have some absorption inside the duct. It will give you a decent performance. You stop a lot of crosstalk in low-level spaces. If you're actually doing high-end studios, you're probably going to need one of these things in the middle. I call them silencers. Some people call them sound attenuators. Some call them duct attenuators. What they are a purpose-built section of ducting that may be 3, 5, 7, 9 foot long. Inside, as you can see from the edge, there are slices of acoustic absorption. And so as the sound travels along the duct, it bounces between those. And yes, I know I described it as a wave, which I said at the start I wouldn't do. But the wave goes down the line, interacts with the fluffy stuff inside of it, transfers some of its acoustic energy into heat energy, and thus decreases the amount of noise that travels down that ducting. That is really the best solution for any time you are concerned about spaces being separated. If you're going to use the same ducting between two different spaces, put an inline attenuator. They literally just sub out for a section of ducting. So this branch above me that's rectangular, you just cut a section out and you can insert one in. It's that easy. So again, if your existing space is struggling with crosstalk, I can hear them and it's coming from the vent. You can slip one of these in relatively easy and they're relatively inexpensive. So something to bear in mind when you're designing a space, if you're trying to improve a space.
So that's different than a Z-duct.
That's different. Z-ducts work on the same principle. They'll be lined with acoustic material, but what they're trying to do is make you go around a corner and back again. But they don't work anywhere near as well as those because the interaction, there's no baffle in the middle. So they interact less with the insulation. That's more trying to make the sound bend. And by bending the sound, it's struggling to go around.
They do help a lot, but I wasn't aware of these.
Yes. Well, this thing, for most low-level spaces, Z-ducts can do quite a lot, especially at mid to high frequencies. A Z-duct is pretty good. Low frequencies is where you start needing to potentially go to one of these inline silencers because they can be designed to target specific frequencies. Z-ducts are a little bit, you can play with them a little bit, but they're just not quite as fine-tunable as an inline silencer.
Those are like Helmholtz traps, basically.
not quite Helmholtz. It's working on, if we get into the details of it. So Helmholtz works on the idea of a cavity, and you send sound into the cavity, and then depending on the wavelength, it cancels itself out as it comes back out the orifice.
Okay.
This works more on the principle of every time you have to turn a corner, certain frequencies will just go straight, hit this top wall, and bounce back down the duct. That's a very simplistic way of putting it, but it's kind of what it's doing. So every time it's turning a corner, the sound, some sound, is being reflected back down the duct. And when it takes this second bend, it hits the back wall and bounces again back down the duct. So you can get some cross like cancellation inside of them, but really they're working on the difficulty of turning corners of certain frequencies, and then the insulation inside of them absorbs. So they're effective at all frequencies because that inner lining, the fluffy stuff inside of it, is going to absorb some of the energy. But you've got big empty space between. There's nothing to stop it, whereas this one actually forces the flow to divide into separate tunnels, which means you get far more interaction with the inner lining on an inline duct. So hopefully that's reasonably clear. I can go into a little bit more if anyone has
And
extra.
one on the left, what's that called again?
So that will be called either a silencer, a duct attenuator, or an inline attenuator.
Okay.
Again, I use silencer because I think that's more of a British term. I think most Americans would call them attenuators. They attenuate the sound. Either way, they silence the noise. That's the idea of them. And like I say, you can make them longer. You can change the internals. So you've got lots of levers to pull to fine tune your design. And when I was doing gas turbine ducting, and when I was doing wind tunnel design, these things, as silly as it sounds, the same attenuator that you would have, the same principles and fundamental way this works is exactly the same as the ones that I would use when I'm designing things that are as big as this room. The ducts are as big as this room. It's the same principles that apply. So you can scale these up and scale them down to suit your application. And like I say, pull a lot of different levers. But in all honesty, every HVAC adjacent company will have a line of these that are standards. So you can actually look up, okay, what performance do I need? And they'll give you some transmission loss data for several standard designs that they just produce en masse. So reasonably easy to get. Obviously, IAC does a range of them, but so do Price Industries and so do Vibroacoustics. Any one of those companies has a catalog that you can look through and go, actually, this would do what I need it to do. System noise, typically misattributed to the fan. So of course you hear a noise, and if you tell your HVAC contractor, I hear a noise, they'll say, oh, it's the motor's too noisy. Again, 9 times out of 10, it is not the motor that is making the noise. It is flow. It is the turbulence of the flow as it comes out of narrow openings. I've put a little thing of what they sound like. So for those playing along at home, this is the noises you should be listening out for. Whoosh is whoosh. Whirring is the whirring of a motor. The motors or the fans, they'll make sort of more of a broadband noise than the turbulent noise of whooshing, as I would call it. Whoosh. The thing that I can hear above my head this entire presentation. This ongoing aerodynamic noise. When you're trying to figure out which one it is and what you can do to treat it, and this is more about existing spaces, check your grills. If it's aerodynamic noise, if you take your grill off, the sound will change. And if it gets quieter, it's because your grill is restricting the flow. And I have genuinely been in spaces where changing the grill to something with a larger open area, the registers, some people will call it, that thing above me that's circular, where the air comes out of, you can actually decrease the noise by 3 dB just by changing the grill, because narrow grills with tight louvers, they spread the air out really well, but they constrict it so much that it becomes a high velocity And that high velocity increases the noise. So that's the number one thing I would say. If you're worried about the noise and you can hear it, remove your grill, see what you hear. If it doesn't change, go a little bit further up your system. Ask your contractor whether you have dampers. They might call them VAR boxes. Sometimes dampers to choke the flow from going to different places, choking the flow increases turbulence in the system. That can create whooshing noises inside the ducting that then comes out your grills. Same thing with your fan speed. Fan might not be making the noise, but because it's running so fast, as it were, it's putting too much flow through a small duct, and thus it creates more turbulent noise and makes the ducting noisy and whooshing, as I would say. And so again, you can quite easily get your HVAC tech to just turn the blower speed down. It might not be as good for cooling performance, but as a check to see what happens, that's the best thing to do. Turn your fan speed down, see if the noise decreases. Open your dampers wide, see if the noise decreases. If it does, it's all aerodynamic noise. Now, if that does nothing, if you remove the grills, you open the dampers wide and you turn the fan speed down, and you can still hear it, then it's the motor. Then I'll agree with you. Yes, it is the motor. That is the problem. But until you've done all those other things, you're probably going to go the wrong direction. You'll go towards the motor when actually you should be going towards how choked the flow is. And again, that can be, if someone's done some crazy ducting runs, bends in the duct can even create flow disturbances. They're trickier to get out of the system, but those three checks, grills, dampers, and fan speed, are your best ways to try and decrease system noise inside your space. Right. Windows. I'm going to sort of be light touch on windows. If you're building new windows, very simply, ask for 1/2 inch or 1/4 inch glass separated by 8 inches. That's it. That's good enough for most studio windows. 1/2 inch glass, 8 to 12 inch gap, gasketing around all the windows, seal it up, make sure there's some fluff in between the two. Bam, there you go, it works. You can buy prefabricated windows. Again, this is where you get into IAC. IAC do a range of prefabricated windows, so do other vendors. Please look around. That is a great way to stop a glass contractor from not doing the right thing. But Russ Berger, who is a well-known studio designer around the world, he insists on all of them being field assembled out of wood, and his rooms test out. So I can't tell you that there's some mythical great thing about having prefabricated windows. I can tell you that if you use a 1/2 inch piece of glass and an 8 inch airspace, you will get a good window. Avoid anyone who uses aluminum storefront windows. Avoid them like the plague. Aluminum is, and as we'll go back to the fundamentals, aluminum is too lightweight to stop sound effectively. It is a lightweight material. Its density is 2,700. The density of steel is about 8,000. So it's, like a third as good as steel for the same thickness. So avoid aluminum. They also have terrible seals involved in them and loads of trim plates, which are just awful. And some people will try and steer you towards triple or quadruple pane windows, thinking if 2 panes are good, 4 panes must be better. Funny things happen at certain frequencies because you're setting up several cavities. And so if those cavities are linear and you've got parallel glazing, so the sound will bounce between the 2 panes of glass, you can end up building a worse window by making it a quadruple pane or even triple pane window than if you were just stuck with 2 panes of slightly thicker glass. So again, sometimes you will end up with a triple pane because you're maybe improving an existing window. If you're doing that, make sure the air cavity between your new pane is different to the air cavity between the 2 existing panes. And make sure you put absorption material around the perimeter. And that's what I mentioned if you're trying to improve existing windows, check your gasketing, replace it potentially. Sometimes glazers chop your gasketing up. You should have a continuous piece of gasketing going all around your pane of glass and recork around the edges. If it's an insulated glass unit, So that's the kind of ones that are here. They've got 2 panes of glass, but they're about that far away. Give up, build a brand new window. You're never going to get the performance out of it. And if you're going to put a second pane of glass onto a single pane glass window, again, follow the guidance above. 8 inches and put foam, put 1 to 2 inches of foam around the perimeter inside the cavity. You've got to try and mop up the frequencies that get through the first pane as it goes through that cavity. So you want to put foam, again, like I said, around the perimeter. If you look at your studio windows, they've all got like a black foam or a black perforate all the way around. That's absorbing the sound between the 2 panes.
I got a question about angle of the glass with reference to the rest of the walls.
Okay.
I've seen angled. What does that buy you?
Okay, now angling is an interesting one. Usually I keep out of this debate
Okay.
because every consultant and every architect has an opinion about sloping glass.
Yeah, I've heard many different ones.
Yes. So if you talk to architects, they'll tell you they slope their glass to reduce the amount of reflections, which is true. But light placing can be just as effective, or a film on your window. If you talk to certain audio engineers, they'll tell you that they're trying to stop hard reflections from getting into their microphone. Also a valid reason to do it, and does have some effect. Really, what it's about is the host facility, in my opinion, and this again is my opinion, and please talk to other experts in the field. What you can gain from sloping your glass, you can achieve just as effectively by placement of your speaker position, the microphone itself, and the rest of the room. Because the hard reflection, it can be broken up in several ways. And if it's a hard reflection that's coming from the back of the room, and I actually don't touch on this because I was talking about sound isolation. When we come to room design in general, you should avoid parallel walls, right? That's if you ever go into high-end studios, they'll have slightly crooked walls in every direction. That's so that you don't set up a standing wave, i.e. what you guys might call a slapback echo, which is where basically the sound wave hits one side to the other and just keeps going back and forth. And it sloshes like sound in a bucket, picking up a wave, making awful spaces in the room. So you go for non-parallel walls, and you know the sloping of the glass of the pane directly in front of you is so that you don't get a hard reflection going from my mouth, hits the microphone, hits the window, bounces back and gets picked up by the microphone. But we're talking about pretty short distances. So you angle on a 5-degree slope, your sound is still going to hit your microphone. Sound doesn't just go straight, it kind of fans, right? So the microphone thing, I mean, it's been done in every studio around the world for years. So I'm not going to say stop doing it. I think it has its place. But the exact reason the person who designs your studio did it, I refuse to comment upon. I have no idea. Let's put it that way.
I've also seen non-parallel glass. When an architect does. Is there any merit to that, or is that just?
That is one. So when we're talking about non-parallel glass, again, you can have a straight inside and a sloped outer.
I've seen
right?
that.
And that's the one that we were talking about with the idea of, well, my microphone's here in my control room, I don't want that. The double slope, and I've seen it in every different configuration, and I've personally sold it in every different configuration. This configuration, that configuration, or even I've sold one that did that. Every single time, the person who was designing the space told me a different reason of why that was happening. Acoustically, it is slightly worse to slope both panes because you have a slightly narrower cavity, which means frequency-wise, higher frequencies will go through that window more easily. So acoustic-wise, it's probably a little bit worse. And also your ceiling at the top and bottom degrades slightly.
Trapezoid's better.
Yeah, so I would personally say that depending on what you're trying to achieve, only slope one pane.
Okay.
If you're sloping both panes, it's probably because you're doing, I don't know, some kind of intercommunication between 2 spaces. Both of them have microphones, in which case it's function over acoustics. It's functionally, we need these panes to be sloped for light or acoustics. And so at that point, you just have to be conscious of it and maybe up the specification of the window a little bit, make the glass a bit thicker.
I've seen it done more for light, actually.
Yes, I mean, the Library of Congress job I just mentioned, they insisted on having sloped windows for light. That's it. Even sloped panes of glass will reflect, but you're less likely to get it. Again, could be change your lighting source and use lower, ambient light, and you can get it to the same level. But yeah, sloping is one of those interesting ones. Trust your designer, but acoustically, I wouldn't. Design your pane of glass correctly, and you'll be okay. Now, Will, I realize I'm running over a little bit. What was my time slot?
Oh, we ignore time here, so
Okay.
keep going.
Anyone who's got family to go home to, wives to kiss, please feel free to leave. I won't take offense, but I'll keep going because I'm getting to the interesting bit. The bit I love, as well known, doors. Doors are fun. Doors are difficult, right? Windows, you put some glazing around them, you caulk them, they work. Walls, you put enough layers of drywall, they work. Doors are the tricky one because they have to move. How do you make something that moves that also seals? And well, and reliably, and repeatably? They are typically the weakest. Sometimes people will blame doors too early. They don't look for their penetrations, they just go, it must be the door. I had WOSU. There was a set of doors between the auditorium and the back of house. They were fire doors, and they blamed the doors. And then we looked above, and all of the fire penetrations hadn't been sealed yet. Quite literally, they were just testing the doors too soon. And so they hadn't actually sealed all their fire penetrations, and consequently, it wasn't the doors, it was the wall. So don't blame your doors straight away, but 9 times out of 10 or 70%, maybe your doors are going to be the weakest point. They are going to be the weakest point, even a really well designed. You can only do so much with a door. When it comes to new doors, I wanted to talk to you about things you should avoid in the industry, because like I said, charlatans and liars exist. And will tell you that things work when they don't. And they sell you a piece of paper that looks good on paper, but doesn't really work in the real world. So I'll give you my top tips for avoiding, when you're building a new space, getting the wrong doors. And I know my company represents a line of doors that are premium and are used around the world in many, many broadcast spaces and everything in between. I'm not steering you towards us. There are other people who have similar, if not equivalent, products. Do not trust any door assembly which has aftermarket perimeter seals. Then ask for a test report. When I say aftermarket perimeter seals, I mean they sell you a frame and then you screw on this piece of metal with a bit of rubber attached to it. And they say, oh, no, it's okay. Those seals are really good. They work with our door assembly. You just screw them in and they'll be great. Aftermarket perimeter seals they're for improving doors. They're not for building proper doors from the beginning. They are typically made with aluminium carriers. So again, aluminum, lightweight, not as good as your steel frame. And they have adjustability, but they're not very good. Ask for a test report. When I say a test report, I mean for the full assembly, frame, door, and seals. You might think that's, surely everyone gives us that. No, some people will give you a test report for just the door leaf. The leaf, the frame. The leaf is the bit that swings, and it can be made of concrete, and you could test it without a frame. And I have seen certain companies, when you ask for a test report, they will send you them testing the leaf, just as a leaf in a wall. No frame, no hinges, no moving. So yeah, guess what? That's a 60. Yeah, until it actually has to seal to anything, and then suddenly the seals become the governing point. And that's the thing, seals are the number one problem with doors. You can build doors out of concrete, but if you leave a 1/4 inch gap around the entire perimeter, it won't test. It will be bad. Do not trust any vendor who gives you reports for which they are just perimeter seals. Again, I have seen this. They say, hey, you buy a hollow metal door and a frame and these seals from us. And here, I've got this test report that says these seals, when screwed in correctly, test out as a 53. Do not trust them. Because unless you're getting the exact same door frame and the exact same door leaf, those perimeter seals could perform like garbage. Just don't trust them. So I've told you what not to trust. I've got one more. Bottom seals, automatic door bottoms. I do not like them. They have their place. You will have seen these in certain spaces. They have a little pin, and as the door swings shut, the pin is depressed, the rubber is forced into the carpet. It seals the bottom gap quite nicely. I say do not trust them because they fail over time, and they also usually indicate that the person selling you the door is selling you a kit of parts. And kits of parts are what you want to avoid. As I say, doors which are sold as an acoustic leaf and an acoustic frame, you want assemblies. You want to ask for a full assembled door, tested as it is. You can get away with this style of door for conference rooms, doctors' offices, low-level stuff. But the minute you're in a broadcast space, they're garbage. They're just not going to do what they're meant to do. When I say kit doors and doors that come as parts, this is genuinely how certain doors will arrive. You've got a frame, a leaf on the left-hand side, and then these are your acoustic seals. They come as a piecemeal assembly. How good is that door? Well, it's as good as the guy who assembles it. It's as good as the guy who hangs it and tells you it's going to work. Again, certain spaces it's fine for. Trying to use in a conference room or a fire station, sure, go for it. When you're doing broadcast, you want things that are sold as a full assembly, if possible, assembled in the factory. You don't have to say that. If you want to hold their feet to the fire, tell them they're going to get it tested. I've genuinely had someone call me up and say that one of my competitors has told me to call you because we told them they were going to test the double leaf STC55 assembly, and even though we've got it on, even though they show it on their website, when they called the guy up, the guy said, if you're going to test it, it doesn't always test out, so you should call these guys. That's how blatant they can be. So you just tell them you're going to test every single opening. Just lie to them. Tell your architect or your GC, if you're building a new space, we're going to test every single wall and every single door. And someone's going to say, well, what's the budget for that? Is it going to be like 100 grand of testing? And you just tell them, no, just tell them it's going to be tested. Put it in the specification. Put it as it has to happen. And you'll scare off most people who sell you shoddy doors. Because they know that when they test it, it won't test out. Always insist on a factory representative on site during the installation. Again, a lot of people will not do this because once they're on site, they're on the hook for making it work or telling you why it's not going to work when it's been assembled exactly to all the factory things. So again, that will weed out some of your more hokey door installers and door providers. That's how you get a door that performs. As I say, if it was me, but I am biased, you would ask for a pre-assembled door, one that has been adjusted in the factory and ships to site as a single piece, so that when it gets to your site, it goes in the wall and it's already been aligned. Thus, no build quality comes into it. But obviously that would be leading you down the route of go buy IAC or their number one competitor. Either way, but this will keep you at least on the right side of getting shoddy workmanship. And again, if you tell them they're going to test it, they actually work a bit harder. They will make sure that the door seals correctly. Some things I didn't put on this slide that are personal preferences. I would steer away from compression seals. Compression seals are those like rubber gasketing things that you see. You'll have had them in certain ones. These doors have them. If you open one of these doors, a little bit of rubber just there. That's all that's providing the sealing on this door. If I'm honest, these doors have as good a weather gasketing as your front door. It's a little piece of triangular rubber that gets crushed when the door gets closed. They're not very good. Compression seals, by definition, have to be compressed. When you want to open a door, if you've compressed your seal enough to seal the gap, you will find it very hard to open the door. Again, there is a university in town that I will not name, where I went through their entire music building. They had just had new doors installed. They were difficult to open. I was there for a completely different reason. They showed me the doors. And what happened is they had adjusted the compression seals so that they were sealed really, really well. The door was, beautifully sealed, except for whenever you tried to push down on the handle, there was so much pressure coming back on the door, you had to jerk the handle down to get it to pop open. Give it a few years and that handle would be dead. What they ended up having to do is back those seals off, which then degrades the acoustic performance of the door. If you're degrading the acoustic performance of the door, what's the point in having an acoustic door in the first place? I would recommend looking for a vendor that gives you magnetic seals, or at least 1 out of 2 seals being magnetic. Yes, they exist. Most people don't provide them. That's why they don't talk about them. Magnetic seals are like your refrigerator door. They will suck the door closed, but not add too much compression difficulty to open the door. So that allows you to get a really good acoustical seal, a self-aligning acoustic seal, more importantly. And just like your refrigerator door that stops hot air and cold air from coming in and going out, same thing with sound. Really good sealing all the way around the door. So that's what I would recommend. But that's a personal recommendation. So you come to me, just like those folks at that university, and you say to me, my door's not performing, Jordan, and you're a bit of a door expert, aren't you? You've installed doors. By the way, I didn't mention this in my opening slide. I have personally installed doors around the world, actually. I was going to say just nationally, but technically around the world. I like to get my hands dirty. It's a personal neuroses of me. I like to get my hands dirty. So if it's not performing, there are 3 reasons your door will not work. 1, the leaf itself is bad. And that is what most vendors will tell you is the fault, i.e. the leaf doesn't perform well enough somehow. 2, there are leakage points. We're talking perimeter seals and bottom seals. And if it's a double leaf door like this one, the astragal, the gap between these 2 doors. And the final one is the installation is poor, i.e. the rough opening in the wall was too big. So how do I find out which one's which? Well, if you had one of those acoustic cameras, you could point it at the door and it would show you where the sound was coming from, whether it was coming around, through the perimeter, or through the leaf itself. Fortunately, most of you probably don't have that. So I'll give you some good rules of thumb. The leaf is usually never the problem, unless it has a window, in which case the window is the problem, not the leaf. If you buy an acoustic door, it will be heavy. Like these doors are heavy, I can just tell. This is a heavy door, right? It's more likely that the sound is going to go through this thin little piece of rubber around the outside or underneath the bottom than it is this heavy-duty fire-rated door isn't stopping enough sound. So again, vendors will tell you you need to replace the leaf. It's the leaf that's the problem. Buy my SBE37 leaf and install it into your existing opening and it will work beautifully. Usually is not the case. Most common performance issue is the bottom seals and the perimeter. Easy rule of thumb, turn the lights off in one space, look at the door. I know it sounds dumb, but I promise you if you go to half of the studios that are having problems with doors, you will find a daylight leak where you can literally see daylight through the door. Again, I'm sort of shaming these doors, but if I turn this light off, I can see daylight at the top and bottom. So I know that that's not, that if you can see daylight, sound can get through. It's like water. It will go through the cracks. So that's the first one. That's a big problem, but it's easy to fix. Adjust your seals, seal up the gaps. Now, when you get to the point where you can't seal anymore, there's a thing called the dollar bill test, where, and this is when you've got compression seals, which again, 50% of you probably have compression seals only. Some of you hopefully have IAEC or an equivalent and thus have magnetic seals. But if you can insert a dollar bill and with your seals adjusted, you struggle to pull the dollar bill out, but you can still just pull it out, you've probably got about the right compression on the door seals. Seems a bit silly, but it's a rule of thumb because a dollar bill is just slippery enough to have enough compression to improve the door, but not too much compression to mess with the lock set like I was talking about earlier. But you're going to turn around to me and say, but Jordan, my seals aren't adjustable. I bought one of those silly doors that don't have adjustable seals and are just basically stick-on seals. What can I do? The answer is you're stuffed. No, I can't give you any clever answer to that. Sorry. You could replace the seals if you can, if they're cartridge-style seals, where they're a big chunk of rubber held in a retainer bracket. You could buy a deeper piece of rubber and just add a bit of extra, a 1/4 inch onto your rubber and make it compress more. But really, at some point, you get to the point where you can't adjust your seals and you can't improve your door assembly. At which point, you may have to buy a new door. If you have the ability to, you could add an aftermarket seal. So say to me, you don't have enough money to buy a new door, which is most of us, you could technically go down the market of buy an aftermarket seal, screw it onto the door frame, improve the amount of sealing that you have. I don't like that. I mentioned poor installation, and this is a big step to take. But when doors are installed poorly, we'll ignore all of the seal adjustments and all of the does it swing right, does it seal correctly. The fundamental problem is the size of the hole in the wall relative to the size of the doors. Again, you're going to say to me, Jordan, that's dumb. Surely all door openings are cut to the right size. And I will turn around and go, oh, if only, if only. So this door has a 2-inch architectural return all the way around it. For those of you at home, look at your doors. You will find that you have what's called the architectural return. They're the thing that sits flat on the face of the wall and stands out a little bit. What that means is that every contractor has 2 inches of slop on either side and across the head to make this door work. So when you're doing regular doors, you just cut it so it's big enough. Like, who cares if there's a 1/2 inch here and a 1/4 inch there and 3/4 at the top? No one's ever going to see it. Just like I was telling you with that electrical box. No one's ever going to see the layers behind. No one's ever going to see the rough opening, as we call it, the hole in the wall. So forget it. I'll just cut it too big and install the acoustic door. Every lab test report you will see, I guarantee you, has been put into a concrete wall with the narrowest, tightest gap possible. Because when we test them in our laboratory, we are trying to get the highest performance rated possible. So we've got the concrete is right up to the edge of my frame. You have to hammer that thing in. So construction, if I have the ability to, and I have the time, the effort, and the money, remove your door if you can. Some doors can't be removed. They have welded frames. The only way to get this door out is to chop it out with an angle grinder. But let's hope that you don't have that. If you can remove the door frame and look and see that the opening's too big, you can easily increase the performance of your door by putting a layer of wood. As simple as that. Piece of 3/4 inch ply or a piece of 1/4 inch ply, however much plywood you need to suck this opening smaller, so that when you reinstall the frame, you actually have the tightest fit possible. And so your acoustic wall that's really good hasn't got just a big old air gap behind what is 14 gauge steel. Because once you've got a gap behind this architectural return, there's nothing there. There's just an airspace that transmits through 2 layers of thin gauge steel. So that's the nuclear option. If you've done a lot of different things and you've even gone out and purchased aftermarket seals and you've screwed them into your door and you're still not getting anywhere near the performance you need and you don't want to buy a new door, remove the door from the opening, look at the rough opening that's there, and what you'll find is usually lots of blocks of wood, shims that make the door look right, but has loads of gap that lets sound through. I should have brought you some issues. So yeah, shoddy installation, just shoddy installation. I said at the start I would mention interior sound environments. I only mention them mainly because certain people will tell you that interior treatments have sound isolation properties. They will conflate NRC, which is a measure of how much sound an item absorbs, with NIC, which is the amount of sound something stops. Now notice, absorb and stop are 2 different functions. Absorb will stop reflections in this space. Absorbing sound will stop slapback echoes and nasty dips in the bass frequencies or something like this. This room has some acoustic paneling. You can barely tell because they've paint matched it, which is quite nice. But all the way around here, there is some absorption so that my voice doesn't boom too much. It still booms because it hasn't got enough treatment. But that absorbs sound. And absorbing sound does not stop sound. Because the amount of absorption is the idea of reflecting off the wall and coming back. 100% absorption means no sound is reflected back into the room. But that sound still goes through the wall. It will still go through the wall. So if, again, rule of thumb, if it attaches to the wall, it will not help sound isolation. I mean attaches to the wall like these panels do. I can put a couple of them on the wall. Vendors might say, yeah, but it'll bring down the noise inside the room, so there'll be less noise to go out. That's kind of true, but it's a little bit of a hoodwinking. If it's fluffy, basically, it's not going to do much in terms of isolation. It will improve the sound quality inside, but it will not stop the sound quality outside. There are some very expensive products available which have mass backers. Again, we're back to mass law. We're way back to the start of this presentation, where they basically put a big piece of vinyl on the back of the fluffy stuff. Again, I say fluffy stuff, it's usually fiberglass or foam, but I call it fluffy because I live in the world of hard things, and fluffy is just what I think of them all as. And that will stop sound coming through the back of it because it's mass. But once you attach it to your wall, it's working on mass law, so you'd have to double the mass of your wall assembly to get a 3 dB boost. Some vendors will argue that it's isolated in some way because they put the mass slightly away from the wall or something. That's a half truth. So maybe it will do a little bit more than 3 dB, maybe. But if you're attaching it to a wall, you've got to treat the entire wall surface from top to bottom, side to side, no holes. So if you do go out and invest in something that is an incredibly expensive mass-loaded vinyl stuck to the back of some fiberglass, you better cover every single inch of the wall. At which point, you're probably at the point where you might as well just put a layer of drywall. And the layer of drywall will do more than that very expensive product. So again, some of you may never have encountered this and you're talking to me, do vendors really say this kind of stuff? The answer is yes. People do say these kind of things. They do say that interior treatments will help with sound isolation. They do conflate absorption with isolation. It's a common mistake throughout the industry, and it's a common misnomer that keeps getting, as unskilled salespeople get taught by other unskilled salespeople, they babble half-truths. So I do always like to point that out. General comments on your interior selections. Thicker is better, as the bishop said to the actress. They absorb more sound at low frequencies than thinner materials, but they also absorb the high frequencies. So if someone says, are you going to put 2 inches of absorption or 4 inches? If you have the space, do 4. 4 inches will absorb the lower frequencies as well as the high frequencies. So why not just go for the slightly thicker thing? Cost-wise, it's usually 6.5 dozen the other. Your stretch fabric system can be retensioned by a credit card or a pizza wheel. This is something fun. It's something that's come out of NPR in DC, who I've been into their studio space many times. And I keep telling the maintenance guys, you know that baggy fabric on your walls? You can fix it. And they go, well, no, we've got to get the special vendor out with the special tool. And they say that they're also got to replace the fabric at the same time. And no, most of your studios will have stretch fabric in. By that, I mean there's a plastic wall track absorption, and then they basically stretch a sheet of fabric and hammer it into the plastic tracks. You can do it yourself. Grab a pizza wheel. That's genuinely the fancy tool they have. Make sure the pizza wheel isn't too sharp, otherwise you will cut the edge off the fabric. But ultimately, you can just stuff it back in. It's designed to be retensioned. It's designed to be pulled out and replaced. And that's another fun thing. If you've got stretch fabric in your space, one, don't be misled by people saying acoustic fabrics. Most fabrics are acoustically transparent, i.e. they do not stop sound enough to stop the sound going into the absorption behind. So do not be misled into believing that you can only have acoustic fabrics. That means that you could potentially print up at any fabric printing establishment something like a logo panel or a temporary panel that you think would be really cool for the back of that photo shoot. Hammer it into your stretch track system yourself, and then take it down and change it out as often as you would like. That's like my weird top tip of the evening. You can retension your own track system, and you can use fabrics that other people don't sell you. Because I don't know whether you've ever looked at the budget for the interior treatment of a studio, but the stretch fabric system, the actual fabric itself can be as expensive as things like $60 a yard, and that's on the low end. So I've seen ones that are $120 a yard. Right? That's a very expensive wall treatment for something that is actually just a piece of fabric. And they're always ugly colors as well. As a side note, they're not nice fabrics. So there you go. There's my top tips for interior sound treatment. Any questions? I'm assuming that most people have more questions about interior sound treatment than isolation. I'm happy to wander down whatever garden path people would like to know about. Okay. Yes, sir.
First, thanks. You've gotten across the point that a lot of improvement in isolation is practical. Are there occasions when you need to go into the field and actually measure the isolation performance of a window or a wall system? And what do? Do you haul in a loudspeaker and an SPL meter?
Exactly correct. So there are people who their entire jobs are acoustical consulting, and 50%, I'd say, of the workload of acoustical consultants is testing in-world STC performance. Like I say, specify that all assemblies must be tested. Most high-level projects that I encounter, they will test a subsection of the doors. So their acoustician will come in. I did the Department of Energy personally. Their facility, it wasn't broadcast, it was just a secure space. And we tested every single wall and door assembly in that place because the government insisted that we did. Someone followed my advice too closely to the letter, unfortunately. And yes, the way you test it is as dumb as it sounds. You take a big old speaker. I use a 200 watt Fender amp for most of mine. I also have a 300 watt PA speaker. People have fancy dodecahedron ones, but ultimately the standard says you can just use any loudspeaker. So you just take a very big amp. So guitar amps are great for it. They have broadband responses. You blast sound on one side and you take your sound level meter and you measure inside and you measure outside. And the difference is what that partition is. But this is where we come into, if you ask me how bad is the door, I can't really test that because what I test is the partition. And that includes all flanking paths. So when you measure in the field, your consultant should be looking at build quality as well as the raw numbers. Because the numbers tell you one thing, but looking at how the thing is actually built tells you where the faults are, because obviously when you see that you're poor performance, you go, well, how do I fix it? So your consultant should always be looking at build quality as well as just doing the test for you. Yes. Some people make good money doing that all across the country. Usually hot and sweaty. They never air condition the spaces well enough, in my experience. Yes, sir?
Again, with respect to interior, and you mentioned glass and windows, is there something that can be put on glass to reduce reflections and still be aesthetically pleasing if you run across any?
There's one product that I know that advertises itself, and it is, in effect, you put slotted glass / they use plastic. And it's like a slotted plastic. And if any of you have seen at the back of your studios, you'll have diffusers. They're the wooden things with holes drilled in them. And what they do is they don't absorb sound, they scatter it. And that's what I've seen as the one product that I really know that does something. But it doesn't absorb. The idea is as it hits that new piece of transparent something, which has lots of different holes, some sound goes through, some sound gets reflected, the sound that goes through hits the glass, bounces back, gets scattered around. And it just makes that window less reflective overall. It disperses the energy in a broader fan. But they're not great. And they're very expensive. I mean, very, very expensive. Last time I checked, they were like $400 for a 2x2 square. They're not great.
Wanted to recount a venue that I worked in, which you may be familiar with, Austin City Limits.
I've seen it on the airline adverts.
Okay. Well, the amps, the PA system won't allow more than 102 dBA.
Okay.
And it pretty much, everything runs at 102. So that's a good reference. It's a pretty substantial SPL. You're in the space with the audience. Walk out the door. As soon as the door shuts behind you, as soon as it latches, you can hear nothing.
Good doors.
I don't know how they did it. I was just amazed. 102, and we're talking like 65 dB.
Yeah.
How do they do it? I mean,
So,
or is there more to it than the door?
no. I mean, obviously, it's a high performance wall to begin with. It's sealed up penetrations between the auditorium and the outside space, but it is really high end acoustic doors. And I will, at this point, amp up IAC acoustics. They may be IAC acoustics doors.
They're heavy, so I can tell you.
They'll be 2.5 or 3.5 inches thick, and they will have double or triple magnetic seals. And the number of seals does matter. A single seal door is not going to get you past, in my opinion, 45, but some people say 50. You need to go to double seals and triple seals. And the weight of the leaf, an STC 61, which is pretty substantial door, 3.5 inches thick, is going to weigh about 350 pounds for a 3x7. For reference, your standard interior door weighs about, 20 pounds. A fire door weighs maybe 50 at a push. These are heavy things. We've installed doors that were, the ones at NBC, they were 10 foot tall by 5 foot wide. I worked it out. They're over 1,000 pounds a leaf. They were still operable. They're heavy, but they're still operable. So it's attention to detail. There's some clever stuff that we do inside, floating septums, isolated front to back. And like I say, triple magnetic seals or double magnetic seals. I can't speak highly enough of magnetic seals. They self-align, they suck the door closed. So you're really sealing up the air gaps, which stop a lot of sound. So I'd be interested, if I go to Austin pretty regularly. As I say, we represent Texas. I have a guy who lives down there who does the sales.
I'd just be interested to put that together because that's very impressive.
I might go in and try and find out who did it. I know Russ Berger did the Dallas Convention Fairground place.
Does anybody here know when that was built? Any PBS people?
Yeah, anyone know? I mean, I'm pretty sure I can just find someone's website who's bragging about doing it.
Yeah, we did several productions there. I just couldn't believe it. I didn't think such isolation was possible.
Well, and this is one of the things I get into a lot with the industry. People don't know what they don't know. And so you go around lots of places and no one tells you these levels of performance are available. And again, I've worked with people before providing them doors and they just go, well, all doors are pretty crap. And then you give them a door that when it closes, it seals the sound out. And they go, oh, I didn't think doors could perform that well. The answer is it's because you were always being, and again, it's not you personally, it's because some architect and your GC hasn't spent the time to make sure you've got the right product. And so they give you meh doors. And so you go through life assuming that only meh doors exist. And then you find a space that has bumper doors. Again, my history of doing stuff with large rotating machinery, there's people who don't believe you can quiet jet engines down. I know you can. There's people who don't believe that I can have a gas turbine running 2 miles away from your house and you wouldn't know. I can. Same with studios, same with attractions. One of the coolest projects we've done recently was, like the Epcot Dome at Disneyland? Well, Comcast did the same thing in their lobby. And it all came about because, as I remember it, the head of Comcast was building that new place and he had a dream about a 360 movie. And he called up his mate, Steven Spielberg. He said, I'd like this. And I'd like it in the foyer, in the entryway of our space. And I want it to be like a dome, 360-degree sphere. It's a sphere planted in the ground, so it's not quite a sphere. And they got in touch with an acoustical consultant, Dave Koch, and said, well, we want this to be inaudible in the lobby. We want you to be, it wasn't even whatever it is, 21 point whatever. It was speakers, almost every piece of the dome had a speaker attached to it. And then a big projection screen. Stopping that kind of sound, most people would think is impossible. They went to 3 vendors and they ended up going with IAC and the people who did the Sochi Winter Olympics because we were the only people who would guarantee performance. And it's exactly the same thing. You can be blasting, it's only a 27-seater theater, by the way. You get in, the 27 seats raise into the air and you rotate around, follow the story. And it's loud. It's Dolby Digital, good stuff, like any cinema. But on the outside, you can't hear it. And there's access hatches to get at the speakers. There's an entryway that has double STC61 doors. There's access hatches in the floor that are STC61. And, if you ever get into Pennsylvania and end up going to Comcast headquarters, you can book a ticket. I think anyone in this room, being, engineers of the broadcasting variety, would find it an interesting experience. Sign up and go see it. I think it's still free. You just have to get your time slot. But yeah, and again, you can witness, very much like you were talking about with Austin City Limits, real acoustic performance in action. Like what can actually be done with prefabricated.
You're in 102 dBA and the door closes, you hear nothing. That's pretty impressive.
Thank you. I'll take credit for everyone in the industry.
I don't know if you were
who can do.
involved, but
I'm going to assume that
I wasn't aware
Might-
that you could build something where no sound would escape, or I couldn't hear it anyway.
Yeah, like I say, it's all about design.
I know one of the things that I learned at one of the places was, and it's hard to do, but you kind of have to be there the whole time the construction's going on, because, we had an occasion where they did all the stuff you're supposed to do. They offset all the seams in the drywall, they did everything else. And when we were close to the end, and I can't remember what was being installed or something, came in with like 5-inch screws, went through every layer to get to the one in the back to make the attachment. Well, now you've got a penetration and a good channel for the sound to travel on.
So, coupling is what we call that, where you create a really great isolation break, either 2 rows of studs or isolation rails underneath your drywall. And then someone comes in and says, well, I need to mount this really heavy speaker. I need to mount it to the studs then. And then they screw, like you say, something that's a 5-inch screw all the way through all your lovely layers of drywall. It's not the penetration so much as the vibration coupling. You've now coupled, and again, with speakers, it's a really big, important thing because they're going to vibrate the wall. If you put them onto the stud with no isolation, you're going to vibrate the stud. So now the vibration's inside the cavity. It's coming from inside the house, right? You can't stop it. So you've got to think when you're trying to attach. What we recommend typically is design your partition to have specific mounting points that are isolated from the stud or freestand everything. Attach it to the floor. Do not attach to your communicating wall. That's how you try and prevent this. And like you say, being present during construction is my number one recommendation. You might not know what you're looking for, but you'll know it when you see it. Big open holes. And more importantly, it just puts the fear of God into them. So they start worrying about, well, that guy with the clipboard's wandering around pointing at things. We better do our jobs right. Sounds silly, but well, if no one has any other questions. Oh, hello. Yes.
Do you all do maintenance on the IAC doors or arrange for that for the areas that you're at?
Yes, we do. Yes, we do.
I wish I had found you a year ago.
I can attest that Jordan has been in this building doing maintenance on the IAC doors and the FM studios downstairs.
Yes. So we are, a year ago, you had a problem. You didn't manage to get
It's no longer my problem.
Oh, that's the problem.
Ian raised his hand and he should not be muted, so.
Sir?
I wasn't sure if the mic was up, so I didn't want to.
We should hear you.
chime in.
Hey, we can hear you.
Great. Well, I just wanted to say this was a great presentation. We're in the process of building a new facility and actually have Russberger Design Group come in and help us design all the acoustic properties for the radio control rooms. And, from a standpoint of an engineer, you don't know what you don't know. And so many of the things he talked about today are just the details and the little things to look for. I've been in the business 35 years. I've got a good sense of what works, but it's those details that really matter, and bringing someone in at the onset to make sure that you don't miss anything. And like he mentioned today, we have the steel framing up. We haven't put the walls in yet, but we will be walking through the process to make sure as they install these, that they are installed right. We put our eyes on it to verify it. And then in the end, have them, Russberger's coming back to do the final acoustic testing. So it's a process, but to get it right, it makes a lot of sense.
I couldn't agree more. Russ is a great guy. His design team are, like I said, they've designed studios around the world. So you're in good hands, is what I would say. And yeah, when he comes back, he'll come back and do a full check of the space. A lot of the times he doesn't do a proper test. He eyeballs a lot of things because he knows when space is working. He knows when they sound wrong, which is the great thing about working with an experienced consultant like Russ or Richard, who also works on his team. So yeah, I can't agree more. Consultants exist for a reason. They have expertise. Use them.
Yeah, there's the other thing I discovered is, it's an ongoing thing after the space is built. I had one occasion at one location where the problem developed later because the door frames were painted later. And the paint stuck to the magnetic seal. And so everything had to be kind of cleaned off and redone.
Yes.
Because what happened was the doors got really hard to open because they were basically glued shut by the paint.
Yeah. That's
You can fix it.
painting is one of those really awkward things. Getting them painted in the factory is a bad idea because when they get installed, they'll probably get scratched. So you say, we'll paint them in the field. Great, except for your painter doesn't understand that those magnetic seals, which are very expensive, again, if they're an IAC door, I'm not going to lie to you, they're expensive pieces of kit to replace because they're unique to the IAC range or to our competitors' range. I'm sure they have their own unique designs. But when they paint them, if you get paint on them, it's a twofold problem. Because one, they can stick the door closed, becoming hard to open. But two, when you call the painter up and say, hey, you painted over my really expensive magnetic seals, would you come in and fix it? He goes, yeah, sure. And then he proceeds to lather them in paint strip, which when you've got a rubberized, the way our magnetic seal works is it's got a rubberized compression behind the magnet. The minute you start applying paint stripper to it, the rubber goes brittle. And in a couple of years' time, you'll start finding that your rubber starts to degrade and break and your magnets start falling out. All because someone didn't put enough painter's tape over a very special piece of we send painting instructions, but 9 times out of 10, people don't read them. So we're at the mercy of the final painter on site not painting over all of our really important pieces. So you're not the only one, is what I'm trying to say. It's happened to many customers from many different necks of the region. And it's a pain. It's a pain to fix. Just don't let them do it.
Yeah, if it happens to you, you will remember, but then when you move on to another gig, the next guy will not know.
It's true. It's true. It's that learned knowledge, unfortunately.
Yeah. One of the other things I would add is, having just gone through a lot of these things, is convincing the people who are responsible for the install or who are supervising the subcontractor that, okay, I'm pointing out this mistake that you've made by using a wedge of cardboard as a shim around this acoustic window. That's not the right way to do it. And convincing them that, yes, that actually will make a difference is very, very difficult in at least my recent experience.
Yeah. Construction-wise, I have been at a construction site and had someone tell me that I've been in this business for 70 years. I know how to hang a door. Okay, thank you. But this is slightly different. You've never hung one of these doors. It's same as all doors, right? Then we get going, and partway through, he genuinely turns to me and goes, wow, this isn't a normal door. Yes, it's not a normal door. It takes precision, and it's acoustic, and it's heavy, and it's got very deliberate design decisions. Windows are the same. And so convincing construction workers that, as we were just talking about, you don't know what you don't know. Unfortunately, lots of construction workers don't know what they don't know, and they don't care that they don't know that they don't know. Right? If it's good enough for a regular door, it's good enough for an acoustic door. If it's good enough for an acoustic window, it's good enough for a normal window, right? It's this inbuilt, just get it built and make it look right. They work to international building code, which means this can be out of level by an 1/8 of an inch, by over 8 feet, it can be out by 1/8 of an inch. That's not good enough for an acoustic door. But that's what international building code is. That's what carpenters have been taught. That's what drywallers have been taught. So they're just going off what they know, and they refuse to listen, which is why, as part of what I said, was make sure you've got a manufacturer's rep on site. If you don't use a factory-approved crew, at least make sure you've got a manufacturer's rep on site. So the rep is in charge of making sure all the design details are as per plan, and that some random drywall crew from Kapitsky or wherever, who has never seen an acoustic door or window before, or built a studio before, follows what was planned. Again, you can only stop so much, but the manufacturer's rep for at least buyout items can stop that. So That's why I recommend doing that. It's these kind of things. You can't use cardboard in an acoustic assembly, even though it kind of packs the hole and I can cork over it. It'll all be all right, right? Anyway, thank you for your time, everyone. I'll let you all go home.
Thank you all very much for coming, and I'll see you next month.